The official start of section 8.3, logarithms as inverses to exponential functions. This is going to be a 2, maybe 3-part series about the introduction to what logarithms are. Exponential functions, turns out you cannot directly calculate the inverse of such functions nicely. So in mathematics, we have to introduce a new terminology, and that is called a logarithm. So exponential functions, they have these special types of inverses called logarithms. And what a logarithm is, it's the logarithm to the base b of a positive number y is defined as follows. If y equals b raised to the x power, then the logarithm to base b of y equals x. So the logarithm to the base b of a positive number y is defined as follows. If y equals b to the x, then the log with base b of y is equal to x. This little 3-letter word here, log, that's short term for logarithm right here. That really means logarithm to the base b of the positive number y is equal to x. So if y equals b to the x, then log base b of y is equal to x. So since exponential functions and logarithmic functions are inverses of each other, then we essentially can do the function composition as follows. We have b to the log base b of x will give us x, and then log base b of x raised to the b power will give us x. The b raised to the log base b power, that will cancel and will give us the x value. So x would equal x, and then the log to the base b power of x to the raised to the b power, that would cancel log base b and the b power and just give us x is equal to x. If you want to think about it as function composition, in this case here, our function f of x equals b to the x, and in this case our function, our inverse function here is f inverse of x equals log base b of x. And in this case, you could see that we're clearly evaluating f of f inverse of x to get x. And then in that case, we're evaluating f inverse of f of x to get x. So now let's do a couple of examples of writing these exponential forms as logarithmic forms. So converting just between exponential form and logarithmic form is what we're doing. So it says write the following in logarithmic form. And if you need to remember how to convert between exponential and logarithmic form, we have y equals b to the x, implies the logarithm to base b of y is equal to x, and y has to be positive. So in the first case, we have 81 equals 3 to the 4th. Our y value is 81, our b value is 3, and our x value is 4. So we would just write that as log base 3 of 81 equals 4. So yeah, log base 3 of 81 equals 4. If you want to think about the base here as the base of the exponent, whatever you're raising to a power, we're raising 3 to the power, so that will be automatically the base. So for 81 equals 3 to the 4th, it's log base 3 of 81 is equal to 4. For 1024 equals 2 to the 10th, y equals 1024. B is equal to 2, and our x is equal to 10. So if we were to write in logarithmic form, we have log base 2 of 1024 equals 10. The base is always 2. Whatever you're raising to a power, that will always be the base. The power will be the x, and the y value will be whatever is left over. So 1024 equals 2 to the 10th, and the logarithmic form is log base 2 of 1024 is equal to 10. And it's important to note that in both these cases that you have to write the base as a little subscript. It's not 2. The 2 is not above in line with the rest of the text or the characters. It's down a little bit as a subscript. If we move on to C, our y value is 1/8. Our b value is 1/2. And our x value should be 3. So then we could write in logarithmic form quite easily. We have log base 1/2 of 1/8 is equal to 3. The last one, the decimal example. Our y value is 0.00243. Our base is 0.3. And our exponent x is equal to 5. So we would get the following logarithmic form. Log base 0.3 of 0.00243 equals 5. Nothing too complicated, just converting from an exponential form into logarithmic form. So now we want to convert logarithmic form into exponential form. Well, just think about it. All we have to do is just identify our b, y, and x. In this case, we have our b is equal to 2, our y is equal to 32, and our x is equal to 5. So knowing that, we can just plug all these numbers back into our exponential form to get 32 equals 2 to the 5th power. The next one, log base 5 of 125 equals 3. Our base is 5. Our y is 125. And our exponent, or our x value, is equal to 3. So then converting this into our exponential form, just replace all the values, and you get 125 is equal to 5 cubed. So just thinking about what these terms really mean, in this case the 2 is our base, 32 is our y value, and 5 is our x value. So just knowing what this here means, what the definition of a logarithm means, can help us change or rewrite a logarithm, something in logarithmic form into exponential form. So for part C, our base is 8, our y is 16, and our x is 4/3. So then we can write it in exponential form as 8 to the 4/3 equals 16. And then for log base 9 of 27 equals 3/2. Our b value is 9. Our y value is 27. And our x value is 3/2. So we can write 27 equals 9 to the 3/2 power. Special case of, actually one of two special cases of logarithms. First one here, and we're going to discuss in section 8.3, is what a common logarithm is. A common logarithm, all it is just a logarithm that uses base 10. So in essence, we would have something like log base 10 of our y value equals x. That's how you would write it at first, log base 10 of y equals x. That's really what a common logarithm is. But since we're mathematicians and just to make life a little bit simpler, we sometimes will omit the 10 as the base when we're using common logarithms, and we'll rewrite it simply as log of y equals x. And what happens is when we see something like this, we understand that the base is automatically 10. We understand that in this case here, we'd be working with a common logarithm. So that's the only way where you can omit the base here is only when it is when the logarithm is using base 10. Otherwise, you would have to show what base it is or whatever your b value is. So just a couple of examples here of common logarithms. We have something like log of 1,000 equals 3. And if you want to take that into exponential form, you'll see 10 cubed equals 1,000. Again, it's understood that there's a 10 right here. That's automatically understood when we say log of 1,000 equals 3, or even log of 0.1 equals -1. It's always understood that there's a 10 as the base, but we just don't write it. So in this case, 10 to the negative first power would be 1/10, which is just 0.1. So it works out in both cases. And for any common logarithm, it'll work out just as well. Turns out you can also evaluate logarithms just by using exponential form. And when I say that, when we have our general log base b of y equals x, we're only going to be given log base b of y, and we're going to try and figure out what value of x is. So we have to rewrite it in exponential form, b to the x equals y. And then we're going to have to manipulate y to be in terms of b raised to some power. That's how we're going to go about solving these, or evaluating these logarithms as such. So if we look at the first one, we have problem A is, first example, log base 2 of 16. We're looking to evaluate that. Just to change it right into exponential form, 2 to what power equals 16. And we're looking to rewrite 16 in terms of our base 2. Turns out it's real easy. We have 2 to the x equals 2 to the 4th power. And we're looking for 2 to the x to be equal to 16. And that can only happen when x is equal to 4. Because 2 to the 4th is 16, so we better have 2 to the 4th power, giving us 16 on the left side of the equality. So x can only be 4. So log base 2 of 16 evaluated will give us 4. I'll rewrite that. And for the next one, B, example B, log base 7 of 1 over 49. We have 7 to the xth power equals 1/49. This 1/49 we can rewrite it, so we have 7 to the x power equals 7 to the -2. That's what that really means. 7 to the -2 is 1 over 49. And then we're just looking for the exponents to equal each other, and that's only true when x is equal to negative 2. Yeah, 7 to the negative 2 is 1/49th. If we plug the negative 2 in for x here, we would get 7 to the negative 2, which is the same thing as 1/49th. So that logarithm, log base 7 of 1/49th, will equal a negative 2. And the last one, log of 0.01. Remember, that's a common logarithm, has base 10 automatically, but we don't write the 10 because it's understood. So in this case, we'd have 10 to some power x is equal to 0.01. Well, this 0.01 is really 10 to the x equals 1 over 100. And then we could rewrite 1 over 100 to get 10 to the x equals 10 to the negative 2 power. And then these two are equal only when the exponents equal each other, so x has to be negative 2, which means our logarithm, our log of 0.01 equals negative 2.